We start now just by introducing the course. And I start by introducing myself. And this is my email. For any questions about the course and maybe wider. So the course is called is titled as Algebraic structures. Structures in integrable systems. And I need to give some comments about the principal object, about integrable system. So I should comment in some words what is the integrable systems. So in fact it is a set of very different subjects in modern mathematics and modern mathematical physics, but each of them are characterized by some notion of the exact solution, of the explicit solution of the problem. So principally, this means the integrability. So it means that we could present a solution of a problem in some different language. More or less, this different language is algebraic or geometric language. So we could explain a solution in terms of some geometrical algebraic structures. We will discuss, for example, the Toda chain. It is a physical problem, mechanical problem, describing some processes in crystals, in one-dimensional crystals, introduced in the framework of the solid, of the physics of solid body. And it appears that to solve this system, so there is some dynamics, some coordinates in this dynamics, and we can construct some object which is a Lax operator. Construct with this Lax operator another object. This is Lax operator. This is in exponential of this Lax operator, and then for this matrix, this is also matrix, an exponential of this object. We should apply what is called the QR decomposition. It is a decomposition of the matrix in a product of the orthogonal and a triangular matrix. Q of.
Yeah, but what is the meaning of this Lax operator?
It's a difficult story, but here we have some dynamics on the phase space. In terms of these coordinates, we construct Lax operator. Some matrix depending on a point of the phase space. And then just decomposing this exponential at the initial time. This is orthogonal. This is upper triangular. And then the theorem says that the solution of these dynamics is described just L of t is Q of t minus 1, L1, Q of t. So this is the initial point. This is an exponential, some trivial operation on the phase space. This is a decomposition. This decomposition, you understand, it is just the Gauss process of orthogonalization of the basis. if you consider the rows of the columns of the matrix as the coordinates of some vectors in the vector space, you could always compose an orthogonal basis by a triangular. Sorry?
L or E, this is
L?
to the power
L0.
and T and
T is just the time. So here the evolution is trivial, just an exponential. It solves the linear equation. This equation is not linear. It describes some interacting particles in the crystal. Okay. This dynamics is linear, but this decomposition introduced this non-linearity in the real physical problem. And then the theorem says that in good coordinates, in the coordinates of the Lax operator on this dynamical space, the solution is like this. So knowing this interpretation of the phase space in terms of the Lax operator, we can, using its algebraic structure, because so the QR decomposition is just the orthogonalization of some object. Using this, we can construct a solution. Another idea, another mathematical structure which can solve a non-linear problem. It was invented in the problem of geodesics on ellipsoid. So we will not discuss in details this case of integrability property, but in this case, this chain of interpretation goes through some algebraic curve, of genus 0, genus G. It's Jacobi, algebraic curve sigma Jacobi variety of this curve, which is just the torus. Okay, and then there is an Abel transform, which goes from divisors on sigma to the Jacobi variety of this curve, and so the solution of the problem of geodesics on ellipsoid here is solved linearly. So this evolution on the Jacobian is linear. So if we can find this transition from one coordinate to another, we can solve the problem. But this example gives an idea of what kind of mathematical structures appears in solutions of the initial problem. Another example. KdV equation. We will discuss this equation in details, but maybe not this way of solution. But also, it is defined in some fluid dynamics, and it is integrable due to many very particular properties. For example, we can construct solutions explicitly to this equation. And one of the way to interpret this integrability is to describe the infinite Grassmannian. Grassmannian is the set of subspaces of some linear space, but we can consider infinite dimensional spaces and, in a sense, half dimension subspaces, in a sense, a Lagrangian or
Yeah, but how
isotropic.
the Rosmanian comes in this discussion is not so it's not obvious.
Even here, it is not obvious that starting from the geodesics on ellipsoid, we should consider some algebraic curves of high genus and the Abel transform. It is not obviously at all. But there is a set of methods which appears in different problems. And we will discuss some of them. We'll discuss some of them. So we will start by some basic definition. So the Lie groups and Lie algebras we have another course on Lie groups and Lie algebras. So we will learn many things in more details. And maybe, but one necessary thing which we will use in the middle of our course, it will be described in the course of differential geometry, because the Lie groups, it is mostly the the subject of differential geometry. And this is the part of algebraic structure which is crucial in the integrability, even in the case of the Toda chain, which I have, from what I have started. Another set of algebraic structure is called by some notation of R matrix. R matrix technique. Technique? No, technique. So it can be understood biliterally by some ansatz of Poisson structure, some ansatz of solutions for the integrable system, but in fact it has a huge underground geometrical and modern algebraic interpretation. So it is related with the notion of the so-called Poisson-Lie group. Groups and quantum groups. Quantum. This terminology and this approach appeared in 80s in the framework of the quantum inverse scattering method. It was developed in the St. Petersburg mathematical physical group with many great mathematicians as Drinfeld, Sklyanin, Semyonov-Tyanshansky, Fadeev, etc. So this technique has a very coherent, very natural geometrical and algebraic interpretation. And we will discuss some aspects of this technique. Another method, another way to think about integrability in some particular situation is by Hamiltonian approach. So we will discuss what is it, and we'll apply it to some situation. And the last part, so all these aspects will be discussed, will be stressed in the case of finite dimensional integrable systems, just classical finite dimensional integrable systems, and then we will discuss KdV equation, KdV hierarchy equation, and maybe some relation between these aspects. So I suppose to demonstrate the bi-Hamiltonian property of the KdV equation, and maybe some R matrix technique which else interact with this subject. Okay. But today we will start with some vocabulary. We will need some just words from group, just from group, from Lie group, Lie algebras, from the theory of representations. It will be enforced during the course of on Lie groups and Lie algebras and differential geometry, just of the fall semester, and as I remember in the spring semester too. But I'd like to use the correct terms, and I will always give you simple example of general terms, and we'll discuss general terms on simple examples. What is the solution? For example, the Toda chain. It describes some set of particles on R with coordinates Q1, Q2, Qn, and momenta, Pi, momenta of particle I. And it is described by equation Qi point is equal Qi plus 1 Q minus 1 Qi. Just like this. So you understand, it is some potential which describe the interaction of particles, and this is a crystal. So this model was invented to describe some effects in crystals. One-dimensional, but however, it's not evident, and this equation is solved by this method. So starting from Qi and Pi, we construct some Lax operator. So in some point, a point here, it is some particular values of all these variables. At some point we construct, we find the point at L0 at this point, we just construct its exponential, then decompose it in QR decomposition, find L of t, which is Q, L0, Q of t, find P of t and Q I of t by the inverse map. And this is a solution of this equation.
Lax matrix is a solution of this.
No, Lax matrix is a good coordinates in the phase space, on the phase space, which allows to apply just the standard
Techniques.
Yes, you find the matrix, you orthogonalize the set of its columns by triangular transformation. You can do it just manually, and it solves the equation. So this step is not evident. So the way how to find the good coordinates in some physical problem is not evident at all. And I should say maybe some discouraging things. Not encouraging, discouraging. that a general dynamical system is not integrable. It is chaotic. So a generic point in a set of dynamical system is chaotic. Integrability is a very particular property. But even if it is integrable, it is not evident to find its solution. And even so, it is very important to find integrable cases, because it is even the subject of the so-called CAM theory, Kolmogorov-Arnold-Moser theory, describing chaotic system, but their behavior in the neighborhood of the integrable point. So the integrable point is a good point even describing a chaotic system. Okay?
But nobody's integrable point is that okay.
In the space of dynamical systems. Okay, so I described what is the solution. So we give just a solution by solving some algebraic equations. Okay, so vocabulary. The first object is a group. Do you need to discuss it? No. Okay. Group homomorphism. Morphism. It's clear. What is the group homomorphism? Subgroup. Subgroup. It's okay. Notions. Examples. Group SN. Symmetric group. That's okay. Symmetric group. GLN group. Elson. Another set of notions. Action of a group on a set. Of a group G on a set X. Is it clear, or you need some comments? What is the action of the group on a set?
So you take an element of the group and then act on the set.
Yes.
It will give some results, maybe some rotation, for example, for SO2 or something.
Okay, with each set X, we can attach the group of automorphisms of the set X. So in the category of set, there are morphisms which are invertible. And automorphism, it is an invertible map from the set to itself. Okay? And this object is a group. It means that if you have an invertible map, the inverse is also a map. It is also invertible, and it is a group. You can always consider composition. It is associative, not necessarily commutative, but so it's a natural group related with the set X. An action of the group G on a set X it is a homomorphism from G to the group of automorphism of X. A homomorphism of groups. This is the definition of the action. But you have to clearly understand what is a homomorphism of groups.
Homomorphism is a group of like map from group to itself. That's it, isn't it?
Yes, but not simply the map. It preserves the structure of the group, which is principle.
Yes, principle of the group.
Yes. So it means that it is the group homomorphism. So I prefer to give you a definition. Phi from G to H is a group homomorphism. If phi of EG is EH, it is the unity element of the group, and phi of X multiplied by Y in G is the same as the multiplication of the images in the group H. Okay. So if two such conditions are fulfilled, then this map is a homomorphism of group. And the action of a group G on a set X is a homomorphism of the group G and the group of automorphisms of the set X. But it's a homomorphism of groups. So, okay. Example. Homomorphism, an action. For example, S3 acts on R2. Do you know how the symmetric group of three elements acts on R2?
I think not exactly.
But you know what is the symmetric group S3?
Like if you have like some triangle, for example, you rotate it, it's like S3.
No. S3 is a group of automorphisms of the set of three elements. Just three elements, and all its automorphisms.
Which is the same.
But it's not trivial and very interesting fact that it is realized by isometries of R2 preserving a triangle. So now if we consider R2 and a triangle, 1, 0. Just then there are three rotations and three symmetries preserving this triangle. And S3 acts on R2 by these isometries. We will discuss it today, just to understand better during the seminar. What else? Some trivial fact, but GL2R acts on R2. Evident? Just by definition, it is the subgroup of invertible linear transformations of R2. Linear transformations are bijections. So in a set of all automorphisms of R2, there is a set of linear invertible automorphisms. It is subgroup of it is a subgroup GL2. Next portion of notions. No, just here. I need to say what is the free action in row of G on X is free. Free. Do you know what is the free action?
It's a long row, I forgot, so I don't know.
I need a word as stabilizer of an element. Definition. Let X as an action, and X is an element of X. Then a stabilizer of X is a set of elements of the group G, such that row of G acting on X is X. Okay. Let us see the what are the stabilizers in this action. The stabilizer of this point is all the group S3. Stabilizer of 0 is just S3. All isometries preserving the triangle preserve its center. All the rotations and all the symmetries, they preserve the center.
What will be the stabilizer of GLR2? I mean, that example.
Even this, yes.
It's the same as the group. I mean, the group will be the stabilizer. Right?
Yes. But it depends on which group we consider. But for this point, S3, the stabilizer GL2, it is also all GL2.
But if we don't consider the center, for example, like 1, 0.
Yes. For example, if we consider this point, the stabilizers will be different.
Yes.
The stabilizer of in the action of S3 of the point 1, 1, it is all only reflection and the unit element in the group. Okay. I will call them 1, 2, and 3. So this subgroup it is given by the unity and the transposition to 3. Okay. All other rotation change this point, and all other symmetries also change this point. And what is the stabilizer of this point in GL2? What do you think? How could you describe the matrices which preserve this point?
So for this, I think we should look at some example.
Okay. They should contain 1, 0 in the first column. It means that they send this point to itself. And here there are some letters, but B is not equal 0. So how do you understand what is it? So it's R2, R2 without R. So it's a plane without an axis. Okay.
Without an axis, the
Yeah.
deflection would be.
No. As a set, this stabilizer is this object. R2 without. I'm sorry. No, like this. It's not it is not a quotient. It's a. We should extract a line from the plane. So the stabilizers depend on the group, on the action, on a particular action. So the stabilizer is this subset, but it is also a subgroup
Subgroup of the group.
of the group. Yes. The stabilizer of an element is a subgroup. It's quite evident. So if you compose to such map, they preserve X. Okay. And an action is phi if for each element of X, its stabilizer Gx is trivial. It contains only the unit element. It means that the action is free. And I also need the definition of transitive action is transitive if for each pair of elements x and y from the set X, it exists an element G such that rho of G of X is equal Y. So you can always reach each element from each other, from any other, by an action of the group. And another object, another notion from this part of actions is an orbit. Definition. Also let it's not G, it's rho. I'm sorry. Rho Gx is an action. Then Ox is the subset of points of X such that it exists an element G such that rho of G of X is Y.
So you're defining the action.
No, it's called an orbit.
Orbit.
It is called an orbit. An orbit. This is an orbit of the element X. It means that you take an element X and you apply all elements of the group to this element.
So this element could be anything, right?
Empty? No, it contains X because in the group you have always a unity element, and unity takes as an identity.
So we take some elements X and then act the group action, and it will give some elements from which group?
No, you get an element of the set. You take an element of the set and you apply all elements of the group. Mm-hmm. And you obtain some subset of elements of the set X. Okay. And this subset is called an orbit of the element X through the action of the group rho. Okay. Mm-hmm. For example, here, if you consider the action of the group S3, what is the orbit of this point? All
the other points.
all the other points. So this action is transitive. You can obtain all, but I'm sorry. It's transitive if you consider just the set of 3 points. But if you consider its action on R2, you obtain only the vertices of a triangle, of the triangle. So the orbit of the cell of this point is the set of vertices of a triangle. Okay. And if you consider this point, what is its orbit? Only this point. Only this point. But if you consider this point, what is its orbit?
I need to draw something.
You have the inversion. You have the inversion and you have rotations. So I think it is these 6 points. 6 points. You see? It is because these points has a stabilizer. The stabilizer is this transposition. And this point has no stabilizers. And that's why its orbit has 6 points as a number of elements of the symmetry group. In fact, it is necessary that you studied these notions. I will use it. So if something is not absolutely evident, I ask you to prepare for the next lectures and for the next seminars, just looking at the Wikipedia or in some textbooks. Okay, next portion of terms, which is absolutely necessary in our course. It is a linear representation of the group. Action of, just a moment, I will write here. An action of the group, orbits, stabilizers, lasers, free and free transitive actions. What else have we discussed? Okay, so it's a portion of notion of the action. Linear representations of groups. I suppose you know the principal thing. It is hugely exploited in quantum mechanics, so it's the principal language of representations of group. It's a space of states. Normally, it's a space of states for some quantum systems. But in our language, linear representation of the group is a map rho from a group to the general linear group of some vector space V. So we fix a vector space and a group of linear invertible transformations, automorphisms, linear automorphisms of the vector space V. And we consider homomorphisms from one group to another group. Our example of the action of S3 on R2 is an example of the linear representation, because we construct a we will discuss it during our seminar today. So why this is a linear representation? Why it's a homomorphism? Okay, but it's a principal example. Else S3 homomorphism to GL to R. Next portion of terms are related with the notion of the Lie groups. Lie group and Lie algebras. Do you know what is the Lie group?
Well, the same, but it follows some constraints, some conditions.
No, it's not the same. It is a group which is also a smooth variety. Smooth variety, it means that you have some smooth atlas on this variety.
What smooth?
Smooth atlas, smooth number of charts parameterizing your variety. So you have smooth coordinates. Smooth means that if you change coordinates, the transformation maps are smooth maps. It will be commented during the course of Troitsky. But principally, it is characterized by some smooth coordinates. And in these smooth coordinates, the multiplication map is a smooth map. This means that a group, some group with some multiplication and inverse map, it is a Lie group. So, definition. G is a Lie group. I will write it, but I have no resources to comment all the terms needed in this definition. G is a Lie group if G is also a smooth variety and multiplication G and the inverse map from G to G, which take the inverse element for an element G, are smooth maps. But these terms need quite deep and important work, and it will be done during the course of differential geometry. But we will work with, principally with matrix Lie groups. And for example, GL and R is a Lie group because the multiplication is given by some polynomial functions. Okay? So how we describe the multiplication on GL and R? This multiplication M, it takes two elements. I will write element A and element B, which are matrices. And it is some matrix A, B. And you know how to describe the matrix elements of this product. A, K, B, Kj, the sum over K. If you take the matrix element as a coordinate on the group GLN, not always, so, but near the unity, for example, near the unity element. Okay. So we could think about the invertibility of this matrix. But near the unity, the matrix elements are good coordinates. And the product, the multiplication on this group, is described by polynomial functions.
So this is a polynomial function?
Yes, it's a polynomial of degree 2.
Okay.
First degree comes from here, and the second degree comes from here. So on this manifold, there are also smooth atlas, smooth coordinates. And in these coordinates, multiplication is given by polynomial functions. They're obviously smooth. But in more general situation, it is not so evident. But we will work principally in matrix groups, where the idea of smoothness of group operations is quite clear. Okay. Lie algebras. Lie algebra definition. G is a Lie algebra. I need more place. I'd like to erase all this and to write down the definition of the Lie algebra. Okay. F G is a linear space. There is a map, and it is defined a map G normally one uses the Gothic letters for the Lie algebras from G to G. Is it clear what is the tensor product of linear spaces? For the moment, we could think about just the Cartesian product, just the direct product of sets, which is bilinear. It's okay. What's bilinear and skew symmetric. Skew symmetric, and satisfied the Jacobi identity. It means that A, B, C plus B, C, A, C, A, B is equal 0.
So you should change the notation of G here also, if G is in the
Yes. Yeah. Bilinear skew symmetric. Do you know an example of the most simple example of a Lie algebra? Okay, more simple. More simple. Known from the first year, from the first university year, from linear algebra, analytic geometry. The most simple example up to me is just R3, with the operation of the vector product. V, W. So if you have two vectors, you construct the vector orthogonal to these ones. This is V, W. So it's orthogonal to this plane, and its value is the square of the quadrilateral given by V and W. Yeah. So the value of V, W is S. This triple is positively oriented, and this vector is orthogonal to this plane. Okay. So this operation is Q-symmetric, because if you change two arguments, you should take the same vector in inverse direction, and it satisfies the Jacobi identity, so it could be verified just directly. Very important theorem, but I'm not sure that you will take this in the program of the fall semester, that the tangent space to each Lie group at a unity possesses a Lie algebra structure.
In simpler terms, if you have an element of the group, we take the logarithm and it will give me the algebra.
Yes. Absolutely. And in inverse direction, you should consider an exponential. So if you have a Lie algebra, just the exponential of its element produces some Lie group. And do you know what is the Lie group corresponding to this Lie algebra?
Lie group corresponding to this algebra?
Yes. Just the Lie algebra R3 with the vector product. What is the Lie group corresponding to?
SU2? SO3 maybe?
SO3. Yes.
The rotation of the
Yes. So these vectors are generators, infinitesimal generators of rotations.
This is also related to SU2, I think.
Yes, they're related, but just this definition is by an exponential produced as SO3. Very good. The examples which we will need for the Lie groups and Lie algebras will be principally the matrix Lie group and Lie algebras. So the starting object is GL and R, G, L, N, C, S, L, N is a subgroup of matrices with unit determinant. Okay. It is a subgroup and it corresponds to the Lie algebra. What else? S, O, N, B, N, R, B, N, T. It's the B plus. It's the subgroup of. It is called the subgroup of Borel subgroup of matrices upper triangular.
What this dot means in SLN?
SLN R and or C else.
Okay.
And here else. B plus minus N plus minus on N R. It is the subgroup of nilpotent upper triangle nilpotent matrices. Means that we have one on the diagonal. Okay, it is also a subgroup. S O. We will not use the unitary group, so it is the principal set of groups, and let us see what is the SLN R. Or maybe GLN R, and the commutator operation on this group. It is given by generators, so it is a linear space generated by elements E, I, J, generators, and the commutator KL given delta GK minus EKJ delta IL. It is useful to keep it in mind, just this formula. Okay. A few other notions. So the exponential map definition. An exponential map from the Lie algebra to the Lie group. So it's in inverse of what I have described in the previous theorem. So we have a relation between Lie group and Lie algebras, just if we consider the tangent space at a unity. So the inverse, it's an exponential map. So in matrix groups, it is described just by exponentials of matrices. Maybe the very good example is to consider the Lie algebra SON, which is the set of A matrices n by n, just the skew-symmetric matrices. The Lie algebra SON is yes, skew-symmetric n by n matrices. It is a good task to verify that it's a Lie subalgebra task. Verify that SUN is a Lie subalgebra of SLN. And the second task is to task 2 to verify that exponential of A from SON is an element of the group SON.
I quite didn't understand the second task. So, where A is an element of the algebra SON, and we need to take the exponential and get S the group.
So, in the terrestrial terms, it means that if AT is equal minus A, then exponential of AT is equal exponential of A minus 1. or exponential of minus a.